My name is Alanda Kriener, and today we're going to be going over lab number 2 regarding the motion of a falling object. In this lab, the falling motion of a crumpled piece of paper wrapped in a disposable face mask is measured in terms of position on the y-axis in time in seconds. The ball of paper is dropped from my height of approximately 1.67 meters and with a mass of a heavily estimated 30 grams. After analyzing the falling motion in Tracker, I created a computational model in GlowScript to model the motion using Newton's second law and including gravity and drag force, with drag force being the upwards force opposing motion and the gravity constant being 9.8 meters per second squared. Some physics principles applied here include the weight force, which is equal to the mass times the gravity constant in the negative y direction, the drag force, which is equal to a constant times the velocity in the y direction squared times the j-hat vector, which we're only looking at the y direction of motion in this case, and Newton's second law, including the velocity and position update equations. Now let's take a look at this motion. While analyzing the data in Tracker, I first specified the frames I was using to analyze the motion to avoid extra frames where the object is still at rest. I then calibrated my height from the object to the ground and established the center of mass in each 0.033 second frame, which potentially wasn't the most accurate as the object started to look more like a blur in the frames. I established the axis of motion to have the origin in the center of the object with the y-axis in the down direction and the positive x-axis to the right. I then marked my start and end times and final falling position. Here are the results from Tracker in two different graphs, the one on the right for a little clearer line. As you can see, the line sort of flattens out at the end, meaning I probably calibrated the center of mass a few times after the object was on the ground already. In order for the computational model to effectively predict the falling motion of the paper ball, I had to update the GlowScript code to match my object's initial conditions and time interval, as well as accurately coding Newton's second law so that the iterative calculations of velocity and position could be done. First, I inserted my object's mass and initial velocity and positions of 0. The net force then is the sum of the weight and drag forces. To apply this net force, I then needed to update the position and velocity equations to be representative of Newton's second law, entering the velocity update equation for the ball's velocity and the position update equation for the ball's position. In my while loop, using the time interval from Tracker, I added my net force components as using Newton's second law, we know that final velocity is equal to initial velocity plus the net force over mass times delta t. The forces acting on this object are the weight and drag forces. The weight force is equal to the object's mass times the acceleration of gravity in the negative y direction, and the drag force opposing the object's motion equaling the proportionality constant for the magnitude of the drag force times the ball's velocity in the y direction squared times the j-hat vector, which in this case is the vector 0, 1, 0, as we are only studying motion along the y-axis. Additionally, I added arrows to represent the drag and weight forces in the model. I calculated the b, or proportionality constant of the drag force, by trial and error to find a b that leads to a calculation close to my observed final position in the y direction of my object. Using a b value of 0.032, the model calculates a final position of negative 1.6839 meters, which is very close to my observed negative 1.682 meters. I also entered 9.8 for the gravity constant and the j-hat vector of 0, 1, 0. Here is the computational representation of the falling object with just a weight force arrow. And here's the computational representation of the falling object with both a drag force and a weight force arrow. Here are my computational model graph results with only gravity acting on the left graph and both gravity and drag force acting on the right graph. Here you can see that the graph with both forces acting on it is slightly more linear, and the final position of the object is much closer to the actual position of the object, implying the drag force is imperative to an accurate motion prediction. As you can see, my Tracker results and the computational model results, though ending in a similar position, vary a lot. Some reasons for error include my mass not being actually weighed and being an inaccurate estimation, inaccurate point of mass calibrations, and my calibration stick not accounting for depth, as my final position in tracker was a position that's actually taller than me. In conclusion, I used Newton's second law calculations in a computational model including drag and weight force to predict the motion of a 30-gram ball-like object in comparison to an object I actually dropped and observed the motion of. While my experiment lacked some accuracy, the model was able to calculate a final position very similar to the final position I observed, and doing this experiment with a better known mass and more careful calibrations could yield even more accurate results.